Hi everyone. This is Chauke speaking, and we'll be going through building and structural construction N6, and the topic will be truss design. All right. So, what is truss design? Let us go back to N2. N2, we dealt with the topic frames as well as in N3 and N5. All right, which is the same as trusses. So now there we were determining the internal forces, which we call them the axial forces, all right, and also the nature, where we'll determine whether it's a truss or it's a tie. All right, so we did that all the way until N5. So that was a preparation for what we're going to be doing here. So designing a truss. So what is truss design? Truss design is where we want to determine the members which will be able to carry the load. We want to go and select the members, okay, from the steel table which will be able to support this load. So we'll take it as in this is what we did in N5 and N3 and 2, where we calculated these forces and also the nature. This shows that this member is under this is a tie, and this one is a truss. This is a strut rather. It's a strut. So now because it's going towards the joint. So now we want to do necessary calculations to go and select a suitable member from steel table. All right. So now I went on to take an example from the book. It's found in page 24. You'll realize that this diagram is not exactly exactly as the one that is in your book. So don't worry about that. But this information is the same. Okay. So now the question says part marked P and Q, which is this one and that one. All right. Sorry. Are single discontinuous angle iron profiles. All right. Fixed both sides to 10 millimeter gussets by means of M16 bolts. So here's your gusset. All right. So they are fixed by this bolt here. So the grade of steel is 43. All right. So question number 1 says select a suitable equal angle for the part marked P, which is this one. Number 2, it says select a suitable equal angle for the part marked Q. All right, which is this one. And we're also told that the total length of part Q, which is this one, is 1,2 meters. All right. So let us go straight to the solution. So now question number 1, we have to design for this tie P. Okay. So number 1, we have to determine the allowable stress. Okay. So how do you go about that? We go to table 20, which in your book is in page 102. Okay. We are given that the grade of our steel is 43. All right. So now when you go to the table, you realize that the first column is showing us the grade. So number 1 there is 43, the other one is 300. All right. So we are given that ours is 43. So we stick to that one there. We move to the second column. You realize that now it has been differentiated by the thickness. So T, the thickness of the member, the first one is less than or equals to 40. The other one is greater than 40. All right. So we are going to assume that the members that we're going to be dealing with will be less than or equals to 40. Therefore, our stress is going to be 155. All right. So that's where that 155 MPa comes from. That is the allowable stress. Okay. Now we go to step number 2. Step number 2, we want to determine the required area. Okay. The required area, it simply means that the area that is going to be able to withstand that load. Remember, the load for P is 45 kilonewtons, right? So the area that's going to be able to withstand, the area of a member that will be able to withstand that force, it is the required area. So I mean, like, it's more like the minimum area. Okay. So now area required is equals to load over axial stress. Okay. Now, what is our load? Load for which is 18 at member P is 45 kilonewtons. So here we want to change it from kilonewtons to newtons. We multiply it by what? By 1,000. So that's where that 10 to the power 3 comes from. So now it's in newtons all over the stress. Alright, our stress is the one that we have determined from step number 1, which is 155 MPa, right? And then if you calculate, you get 290 millimeters squared. Okay, so now here they are converting millimeters squared to meters squared, which was not necessary. But if you want to do that, you have to divide this 290 by a million. All right, it won't be 1,000. Why? Because we're dealing with a area here. We're dealing with an area. All right, so it's gonna be 1,000 squared, which is a million. All right, so we get that value there. So now step number 3, we are going to choose an angle ion. So this one, it is your own choice. Here they chose 50 by 50 by 5 angle ion. All right, remember, why is it 50 by 50? This one, it shows that it's an equal leg, as they told us, right? The question that we must select what? The equal angle or the equal leg. All right, so now they chose this one here from the structural steel table. So you must have that booklet with you as you go through this example. So now I've just taken only this page, all right, which is page 12. Okay, you see there, angles equal leg. All right, we do have an equal leg. So how do you see that? You'll find that your H and B are equal. All right, so here's your H, here's your B. Okay, so now, so they are equal. Okay, so those are your legs. So unequal, we find that this one is not equal with that one there. So what did they select? They selected this one here, 50 by 50 by 5. All right, so this is the one that they've selected there. You can choose any one. I could have selected 60 by 60 by 5 by, or 60 by 60 by 8 or by 10. It's your choice. All right, it's your choice. So what you're going to get in the end is the one that will show or determine whether your selection is fine or not. All right, so there's no exact indication as far as which member you're going to select. All right, so let's go to step number 4. Remember, we have selected 50 by 50 by 5, right? So step number 4, we want to determine the effective area. All right, so we are directed to clause 9,2,1, which is in page number 102. All right, so here's you'll find this formula here. All right, effective area is equal to 3 area 1 squared plus 4 area 1 multiplied by area 2 all over 3 area 1 plus area 2. All right, now I've extracted this one from page 102 as well. All right, so area 1 is equals to what is the net sectional area of connected leg, underline that one, connected leg, based on gross sectional area. All right, which is equals to T into B minus T over 2. All right, so this is area 1. This is area 1. Then now area 2, it is what? Sectional area of the unconnected leg. All right, so this is T into H minus T over 2 into. Okay, now B is the length of the connected leg. Okay, let me show you here. B is the leg of the connected leg. So B is the leg of the connected. So this is the connected leg, right? And then h is the length of the unconnected leg. All right, so here's your h. This is the unconnected leg. All right, probably it's connected to your gusset plate there. Okay, so this is the leg that is connected to your gusset plate. All right, and then t is the thickness of the leg. All right, so here's your t here. So t is the same throughout. So t here is your t. All right, so according to our selection, you remember that your h is 50 and your b is 50. Okay, so they are equal. All right, and then your t is 5. All right, so h is equals to b. So if h is equals to b, then now area 1 will be the same as area 2. Okay, having that in mind, now let us calculate area 2 first. Why? Because it's the unconnected leg. All right, so area 2 is equals to t into h minus t over 2. All right, which is equals to t, which is 5, h is 50 minus 5 over 2, and then we get 237.5 millimeters squared. Okay, so this is our area 2, the unconnected leg area. Okay, so then now we go to area 1. Okay, this one. Remember, area 1 is equals to area 2. All right, but this time around, the problem is this. Now, this is the connected leg, so it has got a hole. All right, so as much as this area is equal to this one, we also have to subtract this one, this empty space here, because of that hole. All right, as it's going to be bolted. So now this area here is d multiplied by t. D multiplied by t. So area 1 is what? Is equals to area 2. All right, but we have to subtract what? The empty space, which is what? D times t. D, which is the whole diameter. T, we already know it, which is 5. All right, so but why is it 18? It is because we are given that the bolt, or the size of the bolt, is 16. All right, so we know that the size of the hole is going to be 2 millimeters more than the size of the bolt. So you add 2 to 16. That's how we get 18. Okay, so now here's our formula, and we say area 1 is equals to this one, 237.5, but we have to subtract this one, and then we say 18 times 5, which is equals to 147.5 millimeters squared. Okay, then now we have our areas. We take those areas to our original equation. We've got area 1 squared divided by 3 plus 4 area 1 times area 2. Don't forget to square area 1. All right, and then all over 3 divided by area 1 plus area 2. Okay, then now you do the substitution, of course, and then you'll get 302.05 millimeters squared. Again, here they are converting millimeters squared to meters squared, which was not necessary, but if you want to do that, you divide by a million again. All right, so now this is the effective area of the selected member. Which member? 50 by 50 by 5. All right, but the required area is what? Is 290. Remember the required area. All right, so then now, and then I mentioned that the required area is the minimum area that we cannot have, or the member that we're going to select should have that area or more than that. All right, so we can see now the selected member 50 by 50 by 5, its area is 0.302 by 10 to the power minus 3, which is greater than the required area, which is 0.29 by 10 to the power minus 3. Therefore, the one that you have initially selected is suitable, meaning that this member will be able to support 45 kilonewton. Okay, that's what it's all about. So we have designed P now. Okay, so now let's continue. Sorry. We are designing for Q now. All right, it's gonna be a different a procedure, okay, from the one that we took for P, all right, or the one that we followed for P, all right, because this one is a strat, all right. And you remember that we are given the length, the total length of that member there, which is 1,2 meters. So we want to determine the effective length. So how do we do that? We go to table 19, which is in page 100 in your book. Okay, you'll find it in page 100. So I've just extracted it here. Here's table 19. Effective length, L of strat with standard condition of end restraints. All right. So now I want us to go to our question very quickly. All right. Let's go to our question very quickly. Now note this. It says parts marked P and Q are single discontinuous angle ion profile. So I want you to underline single discontinuous. Okay, it's only discontinuing only at one point or one side. Okay, so now that is going to guide us when we come to table 19. All right, single discontinuous. All right, if you look at, so that's the condition. So let's look at the conditions here in table 19. So condition number 1 said effectively held in position and restrained against rotation at both ends. No, this is not it. Effectively held in position at both ends and restrained against rotation at one end only. Single discontinuous. All right, let's look at this one. Effectively held in position at both ends but not restrained against rotation. All right, so this one is not restrained against rotation in both ends. So now, but ours only, it is only discontinuing only on one side. All right, so that's how it's about it. So it's restrained against rotation at one end, single discontinuous. So we're going to use 0.85 L. So the factor is 0.85 there. So that's how we come to this one. So effective length is equals to 0.85 divided by L, which is 1.2, and then we get 1.02 meters. All right, I want you to take note of the last block's question paper, that is November 2019. All right, you had this question or Truss question, but then now the condition was different from this one. The condition was that it is discontinuous in both ends. So now you were gonna use 0.7. All right, you were gonna use 0.7, not 0.85. All right, because that one, it is restrained in at both ends, discontinuous or in both ends, or in both sides. All right, so the question was something like that. All right, so now that we have our effective length there, we go to step number 2. Step number 2, we're going to choose an angle ion. Right, this time around they decided to choose what, 50 by 50 by 8 millimeters. All right, angle ion. We will go to it just now. So they chose 50 by 50 by 8 millimeters angle. Again, you can choose anyone, does not matter. All right, the answer in the end is the one that will tell you that whether your choice is okay or not. So now let's go to step number 3. Step number 3, we are going to check the allowable stress. All right, the allowable stress is more like the maximum allowable stress, meaning that anything less than that is not gonna be suitable, or let me say anything more than that. Okay, So now let's have a look at the length here. This is the effective length which I've calculated, which is 1020. Okay, 1020 millimeters. So we're converting 1,02 meters to millimeters. All right. The reason why is because our radius of gyration is in millimeters, so the units must be the same. All right. So what is a radius gyration? We want to go to this angle ion. Okay. So some of the steel tables is RV, some is gonna be IV. All right, it's always gonna be I. We'll discuss why it's V. All right. So let's go to our steel table. All right. So steel table is here. So what was the choice? The choice is 50 by 50 by 8, right? Now the radius of gyration is this small I here. All right. So for the angle ions, all right, we have 3 of the axes. All right. So I've got this one, XX and YY is the same. All right. And then we've got UU and we've got VV. All right. So now we have to go and check the radius of gyration. All right. So let's go to the first one. The first one, YYXS, is 14,8. The other one is 18,6. The last one is 9,63. All right, so we choose the smallest. This is the smallest of the 3. All right, we choose the smallest. And why is the smallest? It's because this axis is the weakest. Okay, so if you can deal with the weakest axis, now at least we have dealt with the whole thing here. So we want to deal with this one because this one is the weakest axis. Okay, now let us go back to our question. So you know that our radius of gyration is 9,63. All right, so if we come back here, there we go, 9,63 millimeters, right? And then the ratio between the two, L over RV or IV, is gonna be what? So it's gonna be 1020 divided by 9,63. All right, so this is a unitless value here. We call it a slenderness ratio, right? So we're getting 105,92. So your answer must not be left with in decimal. Okay, so now you we are going to round this 9, and then it will become 0, 106, right? So if this one here, number after the comma, is less than 5, we're gonna take it as it is. So let's say if it was 105,4, it was gonna be 105 and leave everything which is after the comma. All right, so now run up to 106. All right, so now you take it as in, like, you break it down, 100 plus 6. So 106 is equals to 100 plus 6. All right, 100 plus 6. All right, I'll show you why you have to break it down. If you come to this table, so you have to go to table 17. All right, so after you have calculated the slenderness ratio, table 17. Now this table 17 says allowable stress on gross section for axial compression. For axial compression. All right, so grade is what? Is 43 steel. Okay, right. So now we don't have 106. That is why we broke it down there. All right, so this is the slenderness ratio. Okay, so now you go down to 100. So we do have 100 here. All right, I said 106 is 100 plus 6, right? And then you come here horizontally. You've got plus 0, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6. All right, and then you come down. You come down, and then that's a vertical, and then now you horizontally go to 100. All right, so that is what 73. So that's how we got 73 as our allowable stress. All right, so this is our allowable stress. So now if you come here, you have to check what? Check the stress in the member. Now, what is the stress that is experienced by the member? All right, so due to this one now, it's going to be 50. So axial stress is equal to 50 over area. Remember, the allowable stress is 72, but the force, the stress within the member is going to be what? This one. So it's force over area. The force, remember from the diagram, force for Q is 50 kilonewtons, right? So we are converting it to newtons by multiplying it by what? 100, right? Area, where do we get this area? From the steel table, all right? Let's go back to that member and see. Let's go back to that steel table. All right, so we selected 50 by 50 by 8. If we go to area, here is the area, area is 0.7413. Don't forget, multiply by 10 to the power minus 3. Okay, so therefore that's our area. So now okay, so now area is 0.7413. all right, multiply 10 to the power minus 3. all right, now we divide the two, all right, and then the answer is 67 MPa. all right, 67 MPa. Then now this is the stress experienced by the member. all right, this is the stress experienced by the member. Therefore now this one here, 73 MPa, which is the allowable, is greater than the stress experienced by the member. Okay, so therefore now the selected leg, which is 50 by 50 by 8, it is suitable. all right, why? Because the allowable stress is more than what is experienced by the member. all right, so that's about it. We have designed our legs. all right, so if we go back to our equation, it means then now that P is what? 50 by 50 by 5, and then Q is 50 by 50 by 8. So that's how we design a truss. all right, so I hope this lesson was of any assistance to you guys. So that's about it. I will see you next time.